Hello everyone, welcome to my channel Cat by Nagendra. So in this video we are going to see basic introduction of this engineering drawing. So what is meant by this engineering drawing? Everything we are going to cover in this video. So just we'll start with this first slide. So in this video we are going to learn what is meant by graphic language and what are the different type of drawings we are having. Then next we'll go here with introduction to engineering drawing, then drawing sheet layouts and what are the drawing sheet sizes, then what are the different type of views we are having, again angle of projections, again dimension arrangements, next limits, fits and tolerances, then we are going to through with these tables, and at last we'll go here with symbols. Now let's start here with different types of drawings. So usually drawings we are having of different types. So as you can see, first we are having here freehand drawing. So what is meant by this freehand drawing means the lines are sketched without using any instruments other than pencils and erasers. It means instead of using any like scale or any instrument, just roughly we will create this sketch by using our own hand freehand drawing. So this we call it as freehand drawing. Here we'll be not having any straight lines or proper shapes. Just roughly for reference purpose we are going to create this freehand drawings. Next we are having here instrument drawings. So instrument drawing is nothing but little advanced of freehand. So in freehand drawing, we are not going to use any instrument, just a rough sketch we are going to draw roughly. But if you are going here with instrument drawing, here we are going to create drawings with the help of like ruler or scale. So or some other instruments to create straight lines or circles or curves or proper things accurately by using some instrument. So only we call here as instrument drawing. Then next, if you go here, we are having here computer drawing. Usually freehand drawing and instrument drawing will be created with by our own hands. But if you go here with computer drawing, these are more advanced than both of them. So here computer drawings are usually made by commercial software such as AutoCAD or SolidWorks or CATIA, etc. So here we are going to create these drawings by using computers, and in computer we need to install some drawing softwares like AutoCAD and SolidWorks. So there we will work on this drawing. So usually we are going to see this computer drawing. So those are old tradition methods. Now we are using computer drawings. Then next if we go here, we should know first of all what is meant by engineering drawing. So usually engineering drawing is nothing but it is a communicating language of engineers which gives clear information about design that includes types of views, dimensions and symbols, etc. It means, let's say for example, I am an engineer, I am having some thoughts in my brain. So that thoughts I need to express and it should be able to understand by other engineer. So directly if I say like this with words, maybe he will be not able to understand properly. So whatever the different type of ideas I am having in my brain, just I will make that represent on this drawing sheet. So just I will provide the drawing sheet to another engineer. So by using that drawing sheet, he is able to understand what are the ideas I am having in my brain. So it is nothing but it is a communicating language of engineers which gives clear information about design. So it includes different type of views, again dimensions, symbols. These are we are going to learn in your future tutorials. Then what is the purpose of engineering drawing? See, why we need to draw engineering drawing? Directly we can express with words, right? So here purpose of an engineering drawing is, an engineering drawing is not an illustration. We are not imagining or we are not going to create that. Whatever the ideas we are having, we are representing properly, and whatever the information I am able to convey, opposite person also is able to take proper information by using this engineering drawing. Then it is a specification of size, shape of a part or assembly. So directly if I tell with words, he'll be not able to understand whatever the dimensions he need to take and whatever the tolerances he need to take and what is the shape he need to create. But if I represent in a drawing sheet, he is able to see that engineering drawing sheet and he is able to understand what is the size of that part and what is the shape of that part or assembly. Then the important information on drawing is dimension and tolerances of all its features. So directly I can tell you can take one cylinder, this much diameter, this much length, but he should be able to know what are the proper dimensions we need to manufacture with that particular part. So everything this will be mentioned in engineering drawing, like what is the size and shape and what are the dimensions we need to take. If you go with one cylinder, what is the diameter we need to take, how much length should be for that cylinder, then what is the tolerance we need to provide. So this all will be included in this engineering drawing. So in simple words we can say whatever the model we are going to create, detailed information about that particular part or assembly design, if it is represented on a sheet or drawing sheet, that sheet we call it as engineering drawing sheet. So in this way, with our own words we can say. Then let's move to next slide. Next we are going to see here engineering drawing sheet layout. Directly if it is a blank sheet, we can't call that sheet as a engineering drawing sheet. So for an engineering drawing sheet, standard sheet layout should be there. As you can see here, so this is a blank sheet. For this blank sheet we are having these borders. So these outer lines we call it as borders. Then here we are able to see A, B, C like these small partitions. This we call it as zones. Then always for this engineering drawing sheet, on lower right corner of the drawing sheet we will be having one tabular column. This tabular column we call it as title block. So title blocks will play major role in this engineering drawing sheet. So again in next slide we are going to discuss about this title block in detail. Then for engineering drawing sheet, borders and zones should be there. Again, title block should be present. In that, we will be having different type of views, different type of isometric views, orthographic projections, sectional views, dimensions, symbols, tolerances, everything specification about this particular part, it will be specified in this drawing sheet. So this is a drawing sheet, engineering drawing sheet layout. Next, let's move to the next slide. Here we are going to use this title block. Yes, we have already discussed, always this title block should be on lower right corner of the drawing sheet, and we have said that title block plays major role in an engineering drawing sheet. Why? Because here in engineering drawing sheet on this title block, whatever this in detail description about a part will be specified in this title block. It means in this title block we will be having what is the part name, as we can see title, and what is the part number or drawing number, and what is the sheet size we need to take, then what is the scale ratio we need to take, and what is the finishing symbol, and what is the material we need to use to manufacture that particular part, and with reference to which angle of projection we need to read that engineering drawing. Entire thing about a particular drawing sheet in detail will be specified in this title block. So only we will tell that title block plays major role in an engineering drawing sheet. So here we will be able to see this, who drawn that particular drawing and who checked that and who approved that on which date. Everything will be mentioned about that particular part in detail here itself. So only we will tell title block plays major role in an engineering drawing sheet. So I hope you have understood this. Then next, here for drawing sheets we will be having some proper standards. So as you can see, for Thailand it is in their language, and for USA we will be having ANSI standards. ANSI stands for American National Standard Institute. Then for Japan they'll use JI standards, Japanese Industrial Standards. Then for UK BS standards, nothing but British standards. Then Australia they'll use AS standards, Australian standards, their own standards. Then Germany will use DIN standards, this Dutch Institute for Normung standards. Then ISO standards, International Standards Organization. So usually in our India, maximum cases we use this ISO standards, International Standards Organization. So next, as we have discussed about engineering drawing sheet, so for drawing sheets we'll be having different type of sizes. So here with reference to this JS standards, as you can see, for A4 sheet we will be having dimensions of 210 into 297. These dimensions are in mm. These dimensions are in millimeter. So for A4 sheet we will be having 210 into 297. So this horizontal dimension of 210 and vertical height of 297 we will be having. So this is horizontal 210 and this is vertical 297. Then for A3 it will be double of this. So for A3 sheet it will get a double. So for A3, as you can see, if you want to remember easily, just if you remember this A4 sheet size, this 210 will come like this, same thing. Then 210 we will make into 2. So 210 into 2 if you make, we will get 420. Again if you go for A2, 420 same it will come here. So 297 into 2 if you make multiply, you will get this dimension. Again for A1 sheet, 594 will be coming here. So this 420 into 2 we will make double plus 1 we will add here for A1 sheet. Again if you go for A0 sheet, same 841 we will get here. Here 594 into 2 plus 1 we will add here. So like this we are able to remember this different type of drawing sheets. Then next we are having here drawing scales. So for drawing sheets we'll be having different type of scale ratios. So designation of a scale consists of the word scale followed by the indication of its ratio. If they have mentioned as scale 1:1, it is for full size scale. So let's enter into previous slide in engineering drawing sheet. I'll show that ratio. As you can see here, scale ratio they will be mentioning here 1:1, 1:2 or 2:1 like that. So it means if they have given scale ratio 1:1, for suppose we are having one rectangular block, let's say for example we are having one square block or rectangular block. This length we are having here 100 and this width we are having here 50. Now if they give here scale as x:1, let's say for example in the place of x I am taking here 2. So 2:1 means, so 1 is the original dimension. So 2:1 is used for enlargement of scales. It means this is the multiplication factor. If they given here 2, so we need to make 2 into 1. So as we have discussed, this length is 100 and this width is 50. So these both dimensions we need to make multiplication with multiplication factor of 2. So while creating this sketch, you need to take, instead of 100, we will take here 200, and here instead of taking 50, we will take here double of that 50 into 2, total 100. So here we will take 200 into 100. Then sometimes if they give here 1:x, so this is for reduction of scales. So to reduce the size, 1:2 in the place of x, if they have given here 2, so in the place of 100 we need to make here by 2 by multiplication factor. 100 by 2 you will get 50. Then again here 50 by 2 you will get only 25. So you need to create the sketch only with 50 into 25 if they give scale ratio as 1:2. Again in the place of 2 if they give 3, again 1 by 3 parts we need to make, and we need to consider with that proper standard scales, and we need to create the sketchup. So that is the meaning of this scale ratios. I hope you have understood this. Let's move into next slide. Next we are going to see here different type of views. So basically if I ask you a question that how many types of views you know, you will tell only front view, top view, side view and 3D view or isometric view you will tell. But here different type of views are there. So orthographic projections we are having, it is nothing but 2D views. Then isometric views is nothing but 3D views. Again next we are having here sectional views, detailed views, auxiliary views, exploded views, broken views. So different type of views we are having here. So one by one we are going to see in our next slides or in our next slides. So just let me go for next slide here. First we are going here with orthographic projections. Now, what is meant by this orthographic projections means orthographic projection is a method for representing 3D object in 2D and it has multiple uses in engineering drawing. So what is meant by this orthographic projection means, let's say for example we are having one 3D object. So for this 3D object, if we are specifying or if we are representing in 2D format, so 3D is nothing but three-dimensional mode. Here we are able to get three dimensions, as you can see, length, then height and width we are able to see. So if we want to represent this 3D object into 2D, into two-dimensional only we are able to see here length and this width, or as length and this height, or as width and height. So just orthographic projection is a method for representing 3D object in 2D. We will represent three-dimensional mode into two-dimension. So this type of 2D views we call it as orthographic projections. Then, so to arrange this different type of views, as you can see here, this is the front view they given, this is the right side view, this is the top view. They arranged this properly. How we need to arrange like that? Just we can keep front view to upside, top view downside, right side downside, right? So proper standards we need to mention. So if you want to mention properly and if you want to represent these views, wherever we want, we can keep all these views like front view somewhere, right side somewhere, top view somewhere, like that. But we should not do like that. So we need to represent in a proper way. So to represent in a proper way, here we will be having introduction of angle of projections. So what is meant by this angle of projection means, basically if we are having here empty space, let's assume we are having one horizontal plane and one vertical plane, and we are having this empty area. With the help of this horizontal plane and vertical plane, we are able to divide this empty space into total 4 parts. That parts here we call it as quadrants. So here this is the first part, first quadrant, this is the second quadrant, this is the third quadrant, and this is the fourth quadrant. Now total we will be having here 4 angle of projections. Why? Because here we are having 4 quadrants. So usually we will be having here 4 angle of projections. So in this 4 angle of projections, we'll call first angle of projection, second angle of projection, third angle of projection, and fourth angle of projection. Why? Because from whichever the quadrants we are able to get that angle of projection, that we call with that name only. Now among this all these 4 angle of projections, usually we will use only 2 angle of projections. Those are first angle of projection and third angle of projection. Why we won't use second and fourth means, now let's see one by one. Now let's enter into here first angle of projection. So what is meant by this first angle of projection means, in first angle of projection, object will be placed in first quadrant. So this is the first quadrant, already we know. So here this is the 3D object. Object is placed in first quadrant. Then we are having one horizontal plane and we are having vertical plane, and we are able to see this object from this side. Assume that we are seeing this object from here like this, and whatever the shape we are able to see here, that shape will be projected onto this vertical plane. We are seeing from here, whatever the shape we are able to see, it will be projected onto this vertical plane. Then let's see from top. If we are seeing from top side, we are able to get this circle and this circle. So the two circles will be projected onto this horizontal plane. Why? Because we are looking from top. Then assume that we are having one more plane here like this. We are having one more plane and we are able to see this object from this side. So if I am looking from this side, this entire shape will be specified here like this, and this plane will be specified. Then again assume that we are having one more plane this side also. This is the front side. Why? Because whatever the view directly we are getting in front of our eyes, that view we call it as front view. So this is the front view. Then if this is the front view, we are able to see this one on right side view. So this is the right plane we are having. If you are looking from here left side, we are able to get that projection on this right plane. Assume we are having one more plane on this left side and we are looking from right side, we will get that right side view on this left side plane. Then after projecting all this front view, top view, left side view and right side view, what we are doing is this horizontal plane we are tilting here 90 degrees in clockwise direction like this. So this horizontal plane, just we are having, assume that we are having one vertical plane and one horizontal plane. This one horizontal plane we are rotating or we are tilting 90 degrees in clockwise direction like this. As I have shown here with this arrow mark, this plane we will make like this. Now this is the front view we are having on top side. If you tilt this horizontal plane downside, these two circles will come below that. Under this we will get here. So in first angle of projection, straight on top we will get here front view. Under that, if make tilt here, we will get top view under that front view. Then this right side plane, again we are making this open like this in 90 degrees. We are making or we are tilting here also in this direction. So this plane will be specified like this and same shape we will get here. It means in first angle of projection, front view will be on top. Under that you will get a top view. Then this usually this is the front view and we are looking from left side, but we are getting projection on right side. So here left side view will be placed on right side of the front view. Then assume we are having one more left side plane here and we are taking right side view. Right side view will be placed on left side of the front view. So I hope you have understood about this first angle of projection. Then next, if I go here with second quadrant, assume we are having one object here, same similar to this we are having here, and we are looking from here. Same shape front view you will get here. And if you look from bottom or if you look from top, you will get same these two circles. But always this tilting plane should be in only in clockwise direction. See, already we are having front view downside. Same plane here, this plane is there and here this plane is there. Same this horizontal plane, if I tilt 90 degrees like this, it will overlap each other. As you can see, if I make it here clockwise direction, these two views will overlap each other. So only here we will avoid this second angle of projection and fourth angle of projection. So we will prefer to use only first angle and third angle. Why? Because if you go with the second angle or fourth quadrant, same opposite views will be we are getting. And while making here rotation of these planes will get overlap each other. So only we will avoid here second angle of projections and fourth angle of projection. So I hope you have understood this. Then let's enter into here third angle of projection. So here one more point, in first angle of projection we use opaque planes. Opaque is nothing but we are not able to see through that. It's like just like thermocol sheet or any some paper or something like that in first angle of projection. But if you go here third quadrant, in third angle of projection, here plane of projection will be placed between object to observer. So here we are using transparent planes. Transparent plane is nothing but we are able to see through that plane whatever we are having behind of that plane of projection. So here object is in third quadrant. We are looking from this side and we are looking this object through this projection plane. So this is transparent plane. We can see through that whatever the actual shape we are having for that object, it will be projected on to this vertical plane. Then again, if you are looking from top, here also we are having transparent plane. Whatever this shape we are able to see from top, it will be represented on this horizontal plane. Then again, assume that one more plane we are having here side and we are looking from this side. So whatever shape we are having here, it will be projected on this right side plane only. And if we are having one more plane on that side, same we will get on the same plane. It means in third angle of projection, this horizontal plane we will tilt same clockwise direction. So this plane will come here and this vertical plane will be straight. So third angle of projection, this horizontal plane we are tilting like this, exactly 90 degrees. So now after making that projections, on top we will get here this top view. So in third angle of projection, on top you will get here top view. Under that you will be having here, this is the front view. Then we are having here one more plane, and this is the front view. This is the left side view. Same this plane we will open like this. Same this plane we are having one vertical and one more we are opening like this. So same thing we will get here. Left side we will come on left side of the front view. Then right side we will come on right side of the front view only. So in a simple word, if you want to say, total we are having here 4 angle of projections. In that we used to use only first angle and third angle. Why we won't use second and fourth means, while rotating the planes or while rotating plane of projections, planes will overlap each other and we will get the same shapes. So only we won't use here second and fourth angle of projections. Then in first angle of projection, object will be placed between plane of projection to observer. So in first angle of projection, object is placed in first quadrant. Then front view will be on top. Under that we will get a top view. Left side will be on right side of the projection. Right side will be on left side of the projection. Whereas in third angle of projection, plane of projection will be placed between object to observer. So here on top we will get a top view. Under that we will get front view. Right side will be on right side of the projection, left side will be on left side of the front view. So these are the differences between first angle and third angle. Same thing, just you can see here in theoretical form. So object is placed in first quadrant, here it is in third quadrant. Then object lies between observer and plane of projection. Here plane of projection lies between object to observer. Same as we have discussed before, everything will be specified here in theoretical format. So if you want, you can just take one screenshot, or if you want, just you can make note, you can pause the video and you can note down this entire thing. Then here, so usually third angle of projection will be used in India more, and these symbols are very important. So sometimes in technical interviews, maybe they'll ask that what is the symbol for first angle and third angle of projection. So this is the standard symbols for first angle and third angle. How to remember these symbols easily means, before only we have seen these examples, or before only we have seen these things, right? So just let me enter into here new slide, existing previous slide. See, in first angle of projection, front view is on top. Under that we are having top view. So just we are making this, we are able to see this vertically. If you tilt and if you make it here horizontal position, so this symbol is there here. This is the front view symbol. Under that we are having top view. So if we are having front view on top, under that top view means this is first angle of projection. Same similar to that, it is opposite here. So in third angle of projection, first we are having here top view. Under that if we are having front view, this is third angle of projection. Like that you can easily remember this first angle and third angle projection symbols. Then next we are going to see here isometric views. So isometric view is nothing but usually we will say 3D views. So here isometric drawing shows parts as three-dimensional mode, 3D views. All the vertical lines stay vertical. All these vertical lines stay vertical. Then otherwise parallel lines are shown at 30 degrees. So in 3D views, we will be having here different types like axonometric views, isometric views. So when we call this isometric and when we call this axonometric means, see, if we are having here isometric views with reference to this ground level, so whatever this inclined lines angle is there, no, so this inclination angle will be exactly 30 degrees on both sides equally. So whenever we are having this inclination between this ground level to this inclined line, which is having only 30 degrees, so in that case we can call these views as isometric views. So here we will be able to see all the three views properly. Then if you go here with axonometric, so whatever this inclination is there, no, that will be different. So here you can see 45 degrees and 45 degrees we are having, and one more we are having, one is 60 degrees and one more is 30 degrees like this. So different type of angles we will be able to see in axonometric views. Overall all these views are 3D views only. In that mainly we will prefer to use isometric views. Why? Because in isometric views we are able to see all the three views properly. So I hope you have understood this. Then we will go for next slide. So next we are having here sectional views. So what is meant by the sectional views means, usually let's say for example this is the top view, and in front view if you are not making any section here, only this whole shapes we will get with dotted hidden lines. So what is the indication for dotted hidden lines means their removal of material is present. But here we are not able to see with which shape material is removed when you mention only with dotted lines. So in such cases we use this section views. We can see here a section view can easily display some of the part feature that are not evident when looking just from the outside. So if you are looking from outside, if you are not able to see the what shape we are having inside, in such condition we will make here section views. So cross section is preferred option compared to hidden lines, as it brings more clarity. If we specify with hidden lines, we will be not able to understand properly. If we make here cut section and if we make here hatching lines, it will give more clarity where material is there and where material is not there. So the cross hatching feature is an indicator for cross sectional views. By looking this cross section or hatching directly, we can say that is a section view like this. So here you can see this is the top view. This section line is passing through this line, again it is going to this line, again it is going to this hole. So this arrow marks plays major role. Now arrow marks we are having towards downside, it means we are looking from top to this cut part. So after making this cut section, and if you are looking from top to this, we are able to see this shape like here. And wherever this cut section of material is present, there we will get hatching, and wherever there is no material, we'll mention here blank like this. So this is section view. Again one more type will be there, section cut. So what is the difference between this section view and section cut means? So in section view, if you are going with the section view, if we are passing this cut section line through this, after making cut section, whatever backside we are having lines of these holes, that also we will get here. As you can see here, there is no material is present, but backside lines we are able to get here. But if you go with the section cut, only cut section of material should be present, and wherever this removal of material is present, there it won't show hidden lines or backside lines. So section cut is there, where material made cut section, only that shape we are able to see here. So that is the difference between section view to section cut. Then let's go for new slide. Next we are having here detailed views. So what is meant by detailed views means, this detailed views be used when we are having complex shape. Now let's say for example one view is there here, and here we are having one countersunk hole and one more simple hole with V bottom. So if you want to create these holes here, we need to specify dimensions, like what is the diameter we want, what is the depth we want, what is the countersunk angle we want. All dimensions if I mention here itself, will be not able to read properly. Why? Because already it is a complex shape and that hole sizes are very small. So if you give all dimensions here only, it will get clumsy and we will be not able to read the dimensions properly. In such case, by using these detailed views, we are able to select a particular area or region. By using detailed views, we are able to select a particular area or region, and we are able to get zoom in portion of that particular selected area, and we can specify here separately like this. Now as you can see here, size is very small, we are getting zoom in portion of that area properly. We can mention all the dimensions here like this. So that is about this detailed views. Same for example one more we are having So we don't know with which shape here material is there, or any chamfer or fillet if any present, we don't know that. So in such case, we are able to select particular area or region, and we are able to get zoom in portion of that selected area, and we can give all dimensions and specifications clearly here. So just everything is there with theoretical form. The detail view gives us a close-up of a selected section of a larger view. This can be especially useful if an otherwise large part includes many important dimensions in a small area. So using detail view improves the readability of these measurements. So readability of these measurements will be improves very well when we use this detail views. So we are able to see all dimensions clearly. Then next we are having here auxiliary views. So what is meant by this auxiliary views means, now let's say for example this isometric 3D view is there. We will assume this is the front view. If you look from front, we are able to get this shape, and if you look from top, we are able to get these two rectangles, and if you look from side, we are able to get these two rectangles here. Now let's say for example we are having different shape on this inclined face. So usually whenever we are having flat faces, we will get all the views properly, but when we are having inclined faces, whatever the true shape lying on that inclined face, we will be not able to see properly from either front view or top view or side view. So in such cases, by using this auxiliary views, we are able to get true shape which is lying on that inclined face. So just we will take projection of that inclined face, and we will specify here separately this type of views, we call it as auxiliary views. Now let's say for example, just let me explain you. For example, this object is we are having here. So if you are looking from front, we are able to get one rectangle, and if you are looking from top, we are able to get one rectangle. Then if you are looking from side, we are able to get this rectangle. Now let's say for example, in the place of this flat object, we are having here inclined. So if you look from top, whatever the circle shapes are there, no, we are not able to see clearly. Why? Because it is showing like this elliptical shape. Why? Because it is a inclined face. So in such cases, whenever we are having this inclined faces, we will take projection of this inclined face like this, and we will show separately. So properly the true shape which is lying on that inclined face, we are able to see clearly by using this auxiliary views. So I hope you have understood about these auxiliary views. Then just you can see here an orthographic view to represent planes that are not horizontal or vertical. It helps to show inclined surfaces without any distortion. So while we are having inclined faces, we will take projection and we will show. So that type of views we call it as auxiliary views. Then next we are having here, let's move to next slide. We are having exploded view. So what is meant by this exploded view means, usually a product or a assembly design will be the complex or combination of multiple parts. Now let's say for example, here we are having one like earbud, or we are having here earphone. So after making all this assembly, we will be not able to see with how many parts are there and which part is assembled to which one. Why? Because it is an assembled part. Let's say for example, same we are having one earbud here. So inside we'll be having many parts, but we don't know how many parts are there and which part is assembled to which one. So in such cases, this assembled part, we will make it here exploded, and we are able to see total how many parts are there and which part is assembled to which one and where it is exactly assembled by using this exploded view. So usually this exploded will be used for assembly designs. Here an exploded view drawing is a picture or technical drawing of an object that shows the relationship or order of assembly of various parts in assembly design. It is used for assembly design. So we are able to see how many total parts are there and which is assembled to which and where exactly it is assembled by using this exploded view for the assembly designs. Then Next we are having here break view. So break view is nothing but, let's say for example we are having one lengthy shaft which is having dimension of some 500 into 600 like that. So that entire view we need to represent in A4 sheet. Usually dimension for A4 sheet we know that 210 into 297. It means horizontal length will be 210 and vertical length will be 297. If we make landscape, horizontal will be 297, vertical will be 210. But dimension for this one we are having here 5000. So if you want to specify this view into that A4 sheet drawing sheet, it is not possible. Why? Because maximum horizontal length there we are having 297, but here we are having 5000. So in such condition, one thing we can go with scales. But if you go with the scale, along with this horizontal length, vertical length also will be reduced. So we will be not able to see that proper shape. So in such cases, we use this break views. What is meant by this break views means, when we are having lengthy shafts or lengthy views, just we are able to make here break like this, and whatever this total length is there, it will be compressed to the selected break area, and we are able to give dimension from starting to ending clearly. So these all different type of views and all we are able to see again in detail in drafting. So just we are going here with the theoretical form. So break view make it possible to displace the drawing view in a larger scale, on a smaller scale, on a smaller size drawing sheet. So you create a gap or break in the view using a pair of break lines. So by using this break lines, we will create a gap between that two parts, two sides, and we will adjust that size and we will mention that view into drawing small sheet. So I hope you have understood about this break views. Then next we are having here different type of dimension arrangements. We are having chain dimension. Chain dimension is nothing but one dimension to one more dimension. Here chain link will be there, like continuous link will be there like this. Then parallel dimension is nothing but one dimension will be parallel to one more like this. See, this is a parallel to this is parallel to this like that. Then combined dimension is nothing but combination of chain plus parallel. Here you are able to see chain dimension also, you are able to see parallel dimension also in combined dimension. Then ordinate dimension. So ordinate dimension is very important. What is meant by this ordinate dimension? In this ordinate dimension, one origin point will be fixed, and for every point, dimension should be calculated with reference to this origin point only. In ordinate dimension, origin point will be fixed. For every next point, dimension should be calculated with reference to this origin point only. So from here to this point in vertical dimension, here to here 500, here to here 1000, like that. Again from here to here this much, again here to here, here to here. The dimension should be calculated from here only. Then coordinate dimension is nothing but, so here we will use coordinate values, x values and y values. See, many points are there. All dimensions if you give here itself, it will get clumsy and we can't read properly. In such case, we will create one tabular column. For first one, x dimension, what is the y dimension, what is the diameter. Again for second one, what is the x dimension, y dimension, diameter. Like that we will specify in tabular column. This is coordinate dimension. Now we will see about this limits, tolerances and fits. So first we will go here with limits. So here in limits we will be having here two types. One is lower limit and one more is upper limit. So here for example, one hole we are having, one shaft we are having, whatever the dimension we are having from this ground level to this limit, we call it as lower limit. So lower limit is nothing but the smaller value between the maximum and minimum permissible sizes of a part is called a lower limit. So usually here we will specify with limits. So dimension from this to this, some dimension will be having, again from this to this will be having more dimension. Whatever we are having here smaller value, that is nothing but minimum value, we call it as lower limit, maximum value we call it as upper limit. Same for the shaft also, same we are having here lower limit and upper limit. Means minimum dimension point is the lower limit, maximum dimension point is the upper limit. So here we are having two types. Then next we'll go here with tolerance. What is meant by this tolerance means the total amount of dimension may vary and is the difference between lower limit and upper limit is called as tolerance. So tolerance is nothing but the difference between lower limit to upper limit. This dimensional difference we call it as tolerance. So here what is the use of tolerance means, let's say for example we need to manufacture one shaft which is having diameter of 50 and which is having length of 200. So by using any machining operation or any lathe operation, we will be not able to get accurate dimension of 50.000. Why? Because maybe it may be a human error or machine error or tool error. We won't get accurate dimension of diameter 50.00. So in such cases, for example, we are having one hole which is having diameter of 50 only, and for shaft also we need to mention accurate dimension of 50. So in such cases, by using machining operation, we can't get accurate dimension. So if you try to insert that shaft into hole which is having accurate dimension of 50, it won't go inside because of dimensional difference. So in such cases, that shaft should be said like rejected and will be thrown away. More material will be wasted here. So to avoid that wastage of material, here we will use tolerance. So for every part, let's say for example for a shaft which is having diameter of 50, we'll mention some tolerance value. So this tolerance value will be taken from standard table for so and so diameter and so length. So we need to maintain this much tolerance that will be specified in standard tolerance table. From there we will mention, let's say for example diameter of 50 plus or minus 0.02 like that. So plus or minus 0.02 means original diameter is 50. So if you get 49.98 or else 50.02, that part is said to be okay and it is used for further purpose. So only we use this tolerance. Tolerance is nothing but the difference between lower limit and upper limit. So we are not able to get accurate dimension by using any machining operation. So in such cases that part will be rejected and material will be wasted. So to overcome that wastage of material, we'll specify here tolerance value like plus or minus 0.1 or 0.2 for the parts. So same tolerance will be given for opposite mating part also. So if we maintain that finishing operation and production operation within that two limits, within that given dimensions, then part is said okay and it is moved for further passes. Then in tolerance we are having here different types. So majorly we will tell here two types. One is unilateral tolerance, one more is bilateral tolerance. So in types, first we are having here unilateral tolerance. What is meant by this unilateral tolerance means, unilateral tolerance is the kind of tolerance in which variation is allowed only in one direction from the specified direction. It means before only we told tolerance means plus or minus we will give, but if you go here with unilateral tolerance, only that variation of tolerance value will be specified on only one direction. Either it may be on positive direction or negative direction. Just you can see some examples here. Original diameter is 1.5, plus value we are having 0.0005, minus value we are not giving anything. So here tolerance is specified only on positive direction. Again if you see here, here also tolerance value is specified only in negative direction. Here we have given only positive direction. Like that, only either on positive side or negative side we will specify tolerance value. That type of tolerance we call it as unilateral tolerance. Then next we are having here bilateral tolerance. Bilateral tolerance is nothing but it is a kind of tolerance in which variation is allowed in both the direction from the specified dimension. Unilateral means only positive side or negative side will give variation. If you go with bilateral, in the name itself is there bi, so two sides. Positive value also will be there, negative value also will be there. Again in these two types, bilateral equal will be there, bilateral unequal will be there. Bilateral equal means positive value also this is the value, negative side also this is the value. If you go with unequal dimension, positive value will be different, negative value will be different. So like that we need to mention this tolerance values. Then along with this one more we are having here, limit dimension specify the largest and smallest acceptable values for a dimension. So usually tolerance will be mentioned separately with the plus or minus, but if you go with the limit dimension, that tolerance value will be added to original dimension. Directly will mention within that maximum and minimum dimension sizes we need to get that part. So here tolerance also is added here. Same here also tolerance value will be specified or tolerance will be added to main basic dimension and it will be specified with largest and smallest acceptable values for a dimension. So I hope you have understood about this tolerance topic. Then next we are having here fits. So fit is nothing but the relation between two mating parts. Let's say for example we are having one hole and one shaft is there. The relation between the two mating parts we call it as fit. So in fit we are having here three types. So those is first one clearance fit, interference fit and transition fit. So first we'll go here with clearance fit. What is meant by this clearance fit means, in clearance fit diameter of the shaft will be less than the diameter of the hole. In clearance fit diameter of the shaft will be less than the diameter of the hole. If we try to insert this shaft into this hole, this shaft will move freely into this hole and here again we will be getting here positive gap. Why? Because diameter of shaft is less and diameter of hole is greater. Freely it will move inside and we will be having here clearance gap also. So this type of fit we call it as clearance fit. Again in this minimum clearance will be there, then maximum clearance will be there. So minimum clearance is nothing but the difference between upper limit of the shaft to lower limit of the hole. This gap we call it as minimum clearance. Maximum clearance is nothing but lower limit of the shaft to upper limit of the hole. This maximum dimension we call it as maximum clearance. Then if you go with the transition fit, here either it may be like clearance fit nor interference fit. It means in transition fit diameter of the shaft will be equal to the diameter of the hole. So here we won't get any positive gap or negative gap. Properly the shaft will be inserted into hole without leaving any gap. So this type of fit we call it as transition fit. Last we are having here interference fit. So interference fit is nothing but opposite to this clearance fit. So here diameter of the shaft will be greater than the diameter of the hole. If we try to insert the shaft into that hole, it won't go and it will remain here negative gap. Why? Because diameter of the shaft is greater than diameter of the hole. It won't go inside. We will find here negative gap. Same here also minimum interference, maximum interference will be there. So minimum interference is nothing but here upper limit of the hole to lower limit of the shaft difference we call it as minimum interference. Maximum interference is nothing but lower limit of the hole to upper limit of the shaft we call it as interference, like maximum interference. So this is about three types of fit. Maybe they'll ask in technical questions like what is meant by fit means the relation between two mating parts is known as fit. Then what are the types of fits means total three types of fits are there: clearance fit, interference fit and transition fit. So just we can explain with the values of diameters of these fits. Then again in fits we'll be having here two systems. One is hole basis system and one more is shaft basis system. So what is meant by this hole basis and shaft basis system means, just you can observe this diagram and you can find this definition. In hole based system, size of the hole is kept constant, shaft size is varied to get a different type of fits. In hole basis system, diameter of this hole will be kept constant and diameter of the shaft will vary to get desired class of fit. So if the shaft size is less than the diameter of the hole size, it will give clearance fit. Again, if shaft diameter and hole diameter are equal, it will give transition fit. If diameter of shaft is greater than diameter of hole, it will give interference fit. So this is about hole based system. Again, if you go for shaft based system, it is opposite to this. Here, diameter of the size or diameter of the shaft is kept constant and diameter of hole will get vary. In hole based system, dimension of hole is kept constant, dimension for shaft will get vary. But in shaft based system, dimension for the shaft will kept constant, hole dimensions will change. So if we are having hole diameter is greater than the shaft diameter, we will get clearance fit. If we are having here hole diameter and shaft diameter equal, we will get transition fit. And if we are having hole diameter is less than the diameter of the shaft, we will get here interference fit. So like that, we will use these two types of fits. I hope you have understood about these limits, fits and tolerances, then about this hole and shaft basis system. Then next we'll be going here with the tables. So in engineering drawing, we'll be having different type of tables. For example, we'll be having hole table. Let's say for example, one plate is there. On this plate, we are having multiple holes. So if you want to create one hole, we need to mention here position, horizontal dimension, how much we are having, vertical dimension, how much we are having, what is the diameter of this hole and what is the depth of this hole. If I mention all dimensions here, horizontal for this hole also, again for this hole, again vertical dimension for all these holes in like individual way, all dimensions will get clumsy and we will be not able to read this diagram properly. So in such case, just we will create one tabular column like this. Now for A1 hole, with reference to this origin point, what is the X dimension, what is the Y direction dimension, what is the diameter we want to give for that hole and what is the depth we need to give. Again for A2 size, what is the X dimension, Y dimension, diameter and depth. Like that, how many holes we will be having, all if we mention in a tabular column, we will be able to read this diagram and dimension specifications properly. So this table we call it as hole table. Mainly it is used for holes while we are having multiple holes. Then one more type of table we'll be having here, bill of material. So usually this bill of material will be used for assembly design. So what is meant by this bill of material means it will give detailed information about an assembly represented in a tabular form is called as BOM, bill of material. It includes part name, part number, description, material, quantity, remarks, etc. So bill of material is used for mainly for assembly designs. So bill of material is nothing but it will give detailed information about an assembly design, like how many parts are there, which part is assembled to which one, where it is exactly located, and what is the material used to manufacture or produce that part, and what is the quantity we are using, and what is the comments for next further process. Everything detailed information about an assembly, it is represented in a tabular column, we call it as bill of material. So you can see here total how many items are there, part name, then what is the material used to manufacture that part, how many quantity we have used, manufactured part number, again comments, everything will be specified in this tabular column. So here also we are having balloons, this we call it as balloons. So this is the first part, again this is the second part, this is the third part, this is the fourth part. Like that we will get entire detailed information about this assembly design in bill of material. Then in engineering drawing, we will be having here different type of symbols too. So first we are seeing here general drawing symbols, like diameter symbol will be like this for used for circles, then sphere diameter, then radius will be mentioned like R, again CR control radius, like that counter bore type symbol, counter sunk hole symbol, depth symbol, again dimension origin symbol, square symbol, reference dimension symbol. Like that, different type of symbols also will be specified in engineering drawing. Then we'll be having here surface roughness symbols also. So after making production, we need to maintain their surface finish. So for that, we'll be having different type of symbols. First one is this opened triangle. So if they mentioned with this symbol, basic surface structure symbol, surface may be produced by any method except when the bar or circle is specified. So here just we need to maintain normal surface like basic surface texture symbol. Surface may be produced by any method. So that we are not able to mention properly by using this method only, we need to maintain that surface finish. By using any method, we can maintain this surface finish. But if they give here with closed triangle and like this, material removal by machining is required. There, removal of material is present by using this machining operation. So the horizontal bar indicate material removal by machining is required to produce surface, and material must be provided for that purpose. If we are having this horizontal line here, so there machining should be done and we need to maintain that proper surface roughness on that particular surface. Then if they have mentioned with this symbol, material removal allowance value in millimeter for X defines the minimum material removal requirement. Same similar to this, here also we need to remove material by machining. In the place of X, we will mention how much depth material we need to remove in millimeter, like this. Then last we are having here this one with circle, material removal prohibited. The circle in the V indicates surface must be produced by process such as casting, forging, hot finishing, cold finishing, die casting, powder metallurgy or injection molding without subsequent removal of material. So here we should not remove any material directly by using production method only. We need to get that required surface finish by using this different type of operations such as casting, forging, etc. Mainly we'll need to focus on three symbols. Just if we are having opened one, there just material should be removed with any production method or any machining operation. Next we are having, if we are having this closed horizontal line, machining should be required. So there removal of material should be present. If we are having here with the circle, here material should not be removed. Directly we need to maintain that surface roughness by production method. Now let's enter into new slide and how to give the surface finish. You can see here surface roughness grades. Usually we will use this operation. Why? Because we need to maintain here machining method. Now in the place of here we need to mention machining method. Either we are going here with the grinding operation or facing or turning operation to maintain that surface finish. Again sampling length we need to mention here. Direction of lay we need to mention here. So direction of lay is nothing but for a reference surface, that finishing operation should be applied parallel to the surface or perpendicular to the surface. That next slide we will see. Then roughness value, how much value we need to maintain that surface finish. Then machining allowance we need to give. So this is a standard table for surface roughness grades. For N1 we will need to maintain this much, for N2 this one, for N3 this 0.1 value. So these are the standard grades. According to that machining method which we are going to create, by selecting these grade numbers we need to mention that how much roughness value we need to maintain. Now you can see here direction of lay. Let's say this is the surface. If they given here parallel symbol, in the place of here direction of lay, if they give parallel symbol, surface roughness should be applied parallel to the surface. Again if they give perpendicular, it should be applied in perpendicular direction. Then x crossed is there in x direction. Then multi-directional is there. So not only in a single direction, in any direction we can make it here multi-directional. Then concentric, it is used for circular objects. Concentric means exactly with reference to center point, all in a circular motion only we need to maintain this surface roughness. Then radial, So in this radial shape we need to maintain. Then non-propellant. So wherever we want, just we can move that grinding tool or finishing tool and we can maintain that surface roughness by using this direction of lace. Then again in engineering drawing we will be having here different type of weld symbols as you can see here. So say square butt weld, single V butt weld, whatever this weld, which type of weld we wanted, we need to mention with this symbol. Just you can see this next slide. So like this we need to mention. So arrow will be there, weld all round will be there. So weld all round is nothing but welding should be done on everything. Like upside also welding should be done, downside also welding should be done. Let's say for example we are having here two objects. Let's say for example we are having here two things. So this is one and this is one. So we need to join these two metal parts like this. So to join this metal, we need to do welding here. So if we are having here two, we need to weld either upside or downside we need to mention. If they have specified here weld all round, welding too should be done upside also, then downside also. It means overall we need to do welding when they mention here weld all round. Then field weld will be there. So field weld is nothing but, so if they have mentioned with field weld, only production method should be done in industry and whatever that welding operation is there, no, that should be done on site. So where we are going to install that, there only we need to do welding. If you take example of boilers, for boilers we'll be having column, base, again for upper we will be having top side. So all if we mention like welding operation in industry only, it is very difficult to carry. Why? Because boilers will be with the bigger size. So in such cases, individual parts we will carry to the site. So wherever we need to install that boiler, there we will do this welding operation. So that is the meaning of this field weld. Welding should be done at site of weld. Then fillet weld symbol. Here we need to mention which type of welding we need to do. Like before we have seen these weld symbols, whichever the type we want, just we need to mention weld symbol here and size of the weld, then length of the weld, how much length we need to do, then tile will be there. So like this we need to mention this welding symbol with specification. Again we'll be having here supplementary symbols. So weld with a flat face. Let's say for example we are having two flat faces like this. Then either welding should be done upside or downside. We need to mention with this. So near side means welding should be done here upside. Far side means welding should be done on downside. Same similar to that, if we are having convex faces, like this too. Welding should be done upside or downside. We need to mention with these two symbols. Then concave face, reverse. So if we are having concave faces like this, so where we need to do welding, we need to mention here by these symbols. So I hope you have understood about these welding symbols and all. Then now we'll see about this GD&T. So usually GD&T stands for geometrical dimensioning and tolerances, as you can read here. So it is a symbolic language used by designer to communicate manufacturing constraints and tolerances clearly. It gives clear information of form and shape of the product. So usually this GD&T will be used along with the dimension. Let's say for example, we want to manufacture or we want to make production of one shaft. Let's say for example I'll take this pencil. So for example this pencil is there. If we want to manufacture this pencil, what we want dimension here, we want here this circle diameter and this length how much we need to create. So if I mention only how much diameter and how much length we want, so just if I give diameter and length, usually I need here straight pencil. But whatever this production is going, no, that production manager did with the same diameter what I have given and with the same length what I have given, instead of making this pencil straight, he created like this inclined. Diameter is same, length also same. So this production part is also correct only, right? No. Why? Because we want here with a straight shape, with this circle shape, we need one straight shaft. So in such conditions, Just normally by using dimensions, you can't define which shape we want. So here we will use this GD&T symbols. So in GD&T total we are having here 14 symbols in 5 categories. So first we can see here form category. Under that we are having here straightness, flatness, circularity, cylindricity. Then under this profile category, we are having here line profile, surface profile. Again under orientation, we are having here angularity, perpendicularity, parallelism. Then under location, position, concentricity, symmetry. Then under runout, we are having circular runout and total runout. So one by one, we will see in the next slides about these GD&T symbols. Then if you want to mention GD&T, we need to follow this shape. So here we will be having one arrow mark. Wherever we want to specify this GD&T, we need to specify with this format. So at the top we are having here dimension. In this block, this we call it as feature control frame. In this feature control frame, first we need to mention what is the geometrical character symbol we need to use. Which type of GD&T symbol we need to mention. That GD&T symbol we need to maintain at first block. Then in second block, if we are having or if we are dealing with circular objects, we need to mention here diameter symbol. Then next we are having here tolerance value. How much tolerance, how much variation we need. So the tolerance value we need to mention here. Then material condition modifier we need to mention here. Either we want maximum material condition or least material condition. Then primary datum, secondary datum, tertiary datum. Total we will be having here 3 datum planes. So according to our requirement, we can use either 1 or 2, or in very rare cases we use all these 3 datum features. Now let's go for next slide to see one by one here. So first we'll go here with, just let me go with next slide here. First we are having here straightness. So where we can use this straightness and how to use means, let's say same example what we have discussed earlier. So here for this cylinder we need axis exactly, it should be straight, but by mistake if it is inclined, this entire shape also we will get here inclined shape. You can see this preview here. So this everything it should be with circle, but here we are getting here in reverse direction, like a double we are able to see. So in such condition, we will mention GD&T like this. So here for this face to this face, we are having here straightness with a diameter of 0.1, means we need to manufacture this shaft, or we need to do production for this shaft by making here tolerance of 0.1 variation, we can produce this shaft. So if you want to like accurate dimension or accurate diameter, we are not able to produce. Either maybe it is because of like machine error or tool error. So in such condition, whatever this tolerance value we are maintaining here, within that we need to manufacture this part. So that is about straightness, when we want exactly straight. Then flatness. What is meant by this flatness means, see for example, one object we are having here. So one object is there, just I'll take this. So this one, it should be, everything should be flat, like we should not have any ups and downs like this. Entire the surface should be full flat like this. So in such condition we can mention here flat symbol, like flatness, with reference to how much tolerance we want to make that flatness. So within this limit, if we make that surface flat place, so there we can mention here flatness symbol, just you can give like this. So flatness symbol, how much tolerance we want. Then next we can go here with circularity. Circularity is nothing but particularly for a cylinder, for a cylindrical objects only, exactly at a particular point, everything it is properly with this round circle shape or any like polygon shape it is there, that we can check by using this circularity. So if you mention circularity, full entire thing it should be with the circular shape only. There should be no deviation in this circular motion or in circular direction. Then cylindricity means, here circularity means that circle shape will be checked only at a particular single position. But if you go with cylindricity, this entire thing should be with the cylindrical shape. Like at one step we will be having polygon, next we are having circle, next we are circle. Like that it should not be. Everything entire through it should be with the circle shape within this given tolerance value. Then next we are having here line profile. For example, we are having one surface. On that surface, if we are having any line profile, so there we can mention here with line profile. Just we are able to specify this line profile within this tolerance zone. Then surface profile means here line profile, here surface profile. Line profile is nothing but exactly on that surface, this tolerance value will be checked along with the single point. But if you go with the surface profile, this entire surface will be checked, and whatever this curvature surfaces are there, we need to maintain that surface within this tolerance zone, this 0.1 like this. So usually these are, it will come with like real-time experience. So just I am able to tell you, or I am making you to understand only in a theoretical form. Then next angularity will be there. So if we are having any angularity between this to this, there we can use this angularity symbol. Let's say for example, so this we call it as datum feature, like A, B, C will be there. This we call it as datum feature. Now if you see here, for this inclined line, we are having here angularity with a tolerance value of 0.3 with a reference to A. So this line to this line relation, we are having angularity with tolerance of 0.3 with reference to this. Like that we can read this GD&T symbol. Then again if you go for parallelism, so this will be, you can see this line and this line we are having relation of parallelism. We are having parallelism relation with a tolerance value of 0.05 with a reference to A. Means for this line we are having parallelism with this much tolerance with reference to this side line, like that. Then again perpendicularity. So let's say for example, for this horizontal line we are having perpendicular relation with a tolerance value of 0.03 with reference to this vertical line with reference to datum A. Just we can mention like this. It means normally if you design this part, right, if you give specification for this production, we will be not having any proper relation between this line to this line. So there we will mention this shape. So if I maintain here perpendicular, properly this line should be horizontal, properly this line should be vertical. If you are not maintaining this, maybe he can manufacture this with parallel relations. So here we are able to see form and shape of the profile. Then next position will be there. So we can use this position mainly for holes. Let's say for example, for this hole or this point, we are having position diameter of 0.1 tolerance with reference to A datum and with reference to B datum. Here primary datum also there, secondary datum also there. Why? Because to maintain this proper position, we need horizontal dimension also, vertical dimension also. So here we are able to give like this. So for this position with the tolerance value of this with reference to this side and with reference to this B side. Then concentricity is nothing but both circles should start with the same center point. So here both cylinders should be with the same center point. Just we can maintain here concentricity with the diameter tolerance variation with reference to A. With reference to this inside circle, outside circle also should be with the same reference to center point. If you want any like variation, that variation should be below 0.05 tolerance zone. Then symmetry will be there at last. So symmetry is nothing but, you can see here, we need symmetric relation for this center object with a tolerance of 0.05 with reference to A. With reference to this total length, whatever the dimension we are having from this to this side, same equal dimension we need on opposite side also. So in such conditions, we can use this symmetric relation. With reference to any central plane or central axis, how much dimension we are having on one side, same if you want on opposite side also. In such condition, we can use this symmetric relation. I hope you have understood about basic information on GD&T. So this is about a GD&T symbol. Then again runout is there, circular runout is there. Runout is nothing but here dial gauge will be placed. Mainly it is used for cylindrical profiles. So dial gauge will be placed here and here cylinder will be placed. This will be rotating like this. Then with the help of this dial gauge needle, if any variation up and down is there with the circular motion, this dial gauge will indicate for us. So there we can use this runout. So we are able to check that circularity position exactly at that particular point. Here for example, this cylinder is there and dial gauge will be placed here needle. This will be in rotary motion, it will be rotating. If any variation is there with the circular position, the dial gauge indicator will be shown and we are able to check proper circularity for the cylinder exactly at that particular position by using this runout. So we need to mention runout with the tolerance value of this with reference to A. Similar to that, we are having here circular runout. Runout is nothing but circularity will be checked only at particular point. But if you go with the circular runout, so entire thing will be checked. Here same dial gauge will be placed and this cylinder will be in rotary motion. Runout means only dial gauge will be placed here and it will be rotating. We will check only at that particular point. But circular runout means this will be rotating and this will be moving linear also. So for entire cylinder we are able to check that deviation by using this dial gauge indicator. So in such cases we can use this runout and circular runout to mention entire the cylinder as straight like this. You can see we should be not having any taper shape like this. It should be with entire circular motion for all this overall length. But in runout means only at particular position we will check here. So like that according to our requirement we will mention this. So I hope you have understood about this thing also. Then this is about basic engineering drawing. So if you really like this video, if you really like this content, please like the video, share to your friends to whom it will be useful, and please subscribe and make your friends to subscribe to whom it will be useful. And if you haven't any doubts regarding this, please let me know in comment box. And if I want to improve anything in this teaching, please let me know in comment box. Thank you so much.